what we want to do now is give some context to the problem solving recipe. Okay, so what we want to do right now is outline a problem solving recipe for solving kinematic problems, and this will go for projectile motion problems as well. Okay, but suppose you have this particular question: a car travels linearly for 240 meters while accelerating at a rate of 0.8 meters per second squared for 10 seconds. What is the final velocity of the car? All right. So, the general problem solving recipe, okay? Now, this is going to be specifically for kinematics, but this general recipe will be useful for almost all types of problems. Now, there might be some subtle changes given the type of problem or the subject content, but in general, this is going to be your basic problem solving recipe. So, step one, draw your diagram. Okay, draw a diagram. Now, we've already done that. I've already done that for you. And as a matter of fact, there's one more thing I want to put here. Okay. And step two, define a coordinate system. This is going to be particularly important when working with vectors. Okay. Number three, list your given information. Okay. So half the battle of almost all physics problems is translating the words into variables. Okay. And then coordinating that information with which variables you need, or which variables then correlate with the correct equations that you need. Okay, so translating the words into variables and then correlating those variables with the appropriate equations. Okay. So I've already defined a coordinate system. We're told that the car travels linearly for 240 meters. Now, I haven't explicitly told you that this is in the x direction, but there's no reason not to put it in the x direction, okay? So I'm going to let the car's motion be positive, all right? So in other words, x initial would be right here, and x final would be right here. Now, what we haven't, well, okay, so let's just go through and list our given information. Okay. And then we'll kind of come back and look at this here in a little bit. But a couple other things here in a little bit. But first things first, 240 meters. Okay. This is a unit of length. And out of your kinematic variables, the only one that has length is displacement. Okay, so that's telling you this is your delta x. $240 meters. Okay. Next, while accelerating at a rate of 0.8 meters per second squared. So that tells you that your acceleration is 0.8 meters per second squared for 10 seconds. Okay, so this is your A, this is your T. What is the final velocity of the car? So I then like to say, okay, what am I solving for? Okay. You can call this whatever you like, but I just list it as solving for. So we want the final velocity. And then you also can have other unknowns. And so here's where we actually need to look at our kinematic formulas. Okay. So I'm including the definition of acceleration here, but from your kinematic formulas, you have the definition of acceleration. You have v final equals v initial plus at. You have delta x equals 1/2 at squared plus v naught t. And you have vf squared equals v naught squared plus 2a delta x. Now note, the first three are vector equations, and the last is a scalar equation. Okay, so we're looking for the final velocity of the car. Okay, so what is the final speed of the car? Now, if we're accelerating, we know that the final speed's got to be larger than the initial speed. But if I look at these kinematic equations, okay, what variables do I have? Well, we have delta x, we have t, we have a, we have v initial, and v final. Okay, so for and we can even break up delta x as a matter of fact. Okay, we could call this x initial and x final just as easily. Okay, so I have up to 6 variables in my kinematic list. Okay, in one-dimensional motion, that is. And so now I need to correlate these variables with my given information and my list of givens and unknowns. And this will allow me to plot out or map out the most advantageous way forward to solve the problem. Okay? Now, one thing to note, we are not told that v initial equals 0, so I cannot assume v initial is 0. Okay? Cannot assume that, and I'm putting 3 exclamation points there to drive the point home. We cannot assume that. So, what that means is v initial is going to go into the state of unknowns. Okay? So, I'm given my displacement, I'm given the acceleration, I'm given the time, and I'm solving for vf, but I don't know v naught. Okay? So now I'm going to write the kinematic equations over here on this slide. So the previous slide won't get quite so busy. And so what we've got, actually I shouldn't write it like that because KE will mean something else later, so Okay. And I'm going to drop the vector symbols on top because we're all in one dimension. This is all in the x direction. The only thing that will happen is plus and minus signs with our quantities. But technically, remember that they do belong there. Oop, that's not correct. Okay. So now the way forward, okay, is to look at your givens, and I'm going to try and color coordinate these. So here I have delta x amongst my givens, and I'm going to underline delta x in my kinematic formulas. Everywhere there's a delta x, I'm going to underline it, right? We're also told that we have acceleration. And so everywhere that there's an acceleration, I'm going to underline it purple. And then everywhere that there is time, I'm going to underline that green. You can color coordinate this however you like, or you can use, if you don't have colors, you can use, different numbered lines or whatever. But this is just to show you, and you'll see the utility of this in a moment, but working through what equation or set of equations is going to be the most advantageous, right? So I'm solving for VF, right? And then I'm going to box my unknowns, so that way it kind of sets them apart, okay? And so now what you can do is kind of collate your information here. So this has two unknowns. Because I'm solving for VF, that is technically an unknown, but it is the thing I'm solving for. This has two unknowns. This has one unknown, but does not contain the thing I'm solving for. And this has two unknowns. And so now you can see these two equations have the same two unknowns. And so what you might be able to do is be somewhat clever and combine the two with some method, okay? So that's what we're going to do. Now, technically, you could solve equation 1. Okay, so let's actually kind of map this out. Solution possibilities. And let's label these equations 1, 2, and 3. One solution would be solve equation 2 for V naught, and then plug into equation 1 or 3. Okay? Or a second solution okay? Or you can combine equations 1 and 3 and eliminate V naught. And that's what I'm going to do, okay? It's about the same amount of algebra either way. In one case, you're solving one equation and plugging it into another one. And in the other case, you're still doing the same kind of thing, but you're going to get the result a little bit more directly, okay? So this is really half a dozen one, six the other. I really don't care which one you use. I just want to show you that the reason I can do this is because equations 1 and 3 contain the same two variables that are unknown. The thing we're solving for and then the thing we don't know, okay? So because they contain the same two variables, that means I can use these two equations directly, all right? So that's kind of the utility of mapping your equations out this way. All right. I'm not going to require you to do this on your homework, but I'm going to highly encourage you to, because it will give you a way of collating your information and then looking at your kinematic formulas and knowing exactly which variables are falling where. Okay. So let's combine equations 1 and 3. So equation 1, it says VF equals V naught plus AT. And what I'm going to do is solve for V naught. And so V naught is just going to be subtracting the AT over to the other side. So VF minus AT. And then plug into equation 3, right? But equation 3 says V naught squared plus 2AX is equal to VF squared. So I need to square this. I don't need parentheses. So this is going to become VF squared minus 2 VF AT plus A squared T squared. Okay? So V naught squared now is going to equal all of this. So I'm going to plug all of that in for V naught squared. So equation 3 would now read VF squared is equal to VF squared minus 2VF AT plus A squared T squared. Whoop. Plus 2A delta X, right? Now my VF squareds are going to cancel out, and I'm going to add this over to this side. So I'm going to get 2 VF AT is equal to A squared T squared plus 2A delta X. And finally solving for VF is going to be A squared T squared plus 2A delta X. And that's going to get divided by 2AT. Okay? Now we can be a little bit clever here and we can cancel out an A. If I factor out an A from the numerator, I'm going to get A times AT squared plus 2 times delta x divided by A times 2t. And so my final algorithm let's see. I can let's look at these each individually. So this is going to be 1/2 AT plus delta x over t, right? So now it's plug and chug. And actually, before we go on, let's look at this, and we will do it over here, but I want to make sure I have it memorized. So VF is equal to 1/2 AT, yep, plus delta x over t. Okay? So now that you've derived some sort of result here, let's do dimensional analysis on it before we go on. And this is going to enable us to claim whether we've solved the problem correct, or at least have a consistent equation, right? So VF carries units of velocity, which is length per time. 1/2 doesn't get units, but acceleration does. So this is going to be length per time squared. T gets units of time. And delta x is going to get units of length. And t is going to get units of time. And L over t squared times t becomes L over t. And L over t. And lo and behold, because these are the same units, I can add them. Therefore, the addition sign is a valid thing. And both of these terms have the same units as the left-hand side. So this is a valid equation. Yay. Okay. So now it's plug and chug. So VF is going to equal 1/2. And coming back to our values, my acceleration was 0.8. T was 10. So actually it might not hurt to write these down. Delta X was 240 meters. A was 0.8 meters per second squared. And T was 10 seconds. Okay. So 1/2 AT. So 1/2 0.8 times 10 seconds plus 240 meters divided by 10 seconds. Okay. So 10 divided by 2 is 5. And 5 times 0.8 is 4. So this is going to be 4 meters per second plus 24 divided by 10, or 240 divided by 10 is 24. And so my final velocity is 28 meters per second. Okay? 28 meters per second. And you should find that same answer if you do it the other way. Solve equation 2 for V naught and then plug that into equation 1. Okay? But I wanted to show you how to combine equations as well. So hopefully this tutorial demonstrates a few things. Number one, helping to translate the words and numbers that you have in a word problem into your variables that you can collate into your givens, the thing you're solving for, and any leftover unknowns. Then how to correlate those with your kinematic equations, and then pick the equation or equations, pick the step or steps needed to solve, and then map out the exact way you're going to go about it. Okay? And then finally from there, doing dimensional analysis on your final derived result, and then solving your problem. Okay? So that is the recipe. All right? That is the recipe. So step 4 is choose appropriate equations. And step 5 is solve. Okay? So there's your problem-solving recipe. Draw your diagram, define your coordinate system, list your given information, choose your equations, and within that step, that is where you correlate your given information with the variables in the kinematic formulas. Then from that, you pick your simplest way forward, and then you solve. Okay? So I hope that's helpful, and we will see you in the next video.